All right, we're continuing with some more limits today. Just a quick little recap. We talked about this one a little bit the other day, but it is a tricky little concept, so I wanted to mention this one again. It's looking at the 1 over x graph. So here's our 1 over x graph. Sometimes it's easier to think of the graph in terms of the limit, and sometimes it's easier to just look at the equation, but in this case, I guess we can do both. This first one up top here, it says the limit as x approaches infinity. So that says x is getting larger and larger and larger and staying positive of 1 over x. So the denominator is becoming very, very large. The numerator is staying at 1. So 1 divided by a very, very large number gets closer and closer to 0. And we can see that from the graph. Right? As we go further and further and further to the right, the graph gets closer and closer and closer to the x-axis. It's getting closer and closer to a y value of 0. Similarly, for the next one, x is now approaching negative infinity, so we're heading out this way. We've got exactly the same thing happening. The denominator is getting very, very large, but has a negative value, right? And we have to be careful of that. We have to be careful when we say large and small, right? The size, the scale of the number is very, very large, but it's also a negative number. So it's 1 divided by a very, very large negative, which gives you a very, very small negative number, but it's still getting closer and closer to 0 each time. So that's why we say the limit here approaches 0, right? You can see it getting closer and closer to the y-axis. Notice in that case, it's getting closer and closer to 0, but it's a negative the whole time. Now with those two limits, they're only one directional limits, right? We're going to positive infinity. You can't go to positive infinity from the right. You can only approach infinity from the left. You can only approach negative infinity from the right. But when I look at this guy, as x approaches 0, I need to consider x approaching 0 from the right. That's how we wrote it, remember? And x approaching 0 from the left. So I guess I can use green again still. So as I approach 0 from the right, that's my graph going this way. And the graph's heading up to positive infinity. And if I go this way, it's heading down to negative infinity. So we could write this, the limit as x approaches 0 from the right of 1 over x is positive infinity. I don't really need that positive, remember. It's not horrible to write it in there. And as we approach it from the left, it equals negative infinity. And the requirement for a limit to exist was that those two values had to be the same, and they're clearly not. Now, there's an issue here that's bugged me, and I've looked it up and actually talked to a couple of my friends at universities. It bugs me that I'm writing, well, it bugs me that I'm writing this equal sign right here, because we kept talking with limits about how infinity isn't a number. So how can we be equal to infinity? And you can't. Right? It's not really fair to say that this equals infinity. This is another one of those ones where we're using the symbols to indicate an idea. We're saying that this limit gets bigger and bigger and bigger forever. And so the way to do that is we can write equals infinity. But again, please keep in mind, when I'm writing that, I'm not saying that infinity is a number. Saying that is very different than me writing that this limit approaches 2, right? If I had some limit and it's approaching 2, that's the number 2. We're getting closer and closer to the number 2. Here, I'm writing equals infinity, but remember, infinity is just an idea. Title, more limits. So we've talked about the idea. Sorry, this is a massive slide, and not one that you need to copy. Okay, we've never copied this one down before. It's just a screenshot of a slide, a page in your textbook. So you can take a look and find it. I can't remember what page it's on, but if you just look in the limit section, you can't miss it. It's a great big table. This has some properties of limits, things that are always true. And we're going to play around with them a little bit. I want to show you how they work with particular functions. They're going to be important a little bit later when we have to do some proofs, so they'll come back into play then. But they aren't things you're going to have to remember. For the most part, actually, they're just going to make sense after we get a little bit further. I'll just mention them here. This one here is, it says the limit as x approaches a. They all say as x approaches a. That's not important. It's just saying as we approach something. Of a constant is just a constant. So what that's saying is if you started with a straight line like that, and your graph, if you said let's say that's y equals 3, okay? So that means that your c value is 3. So if I said let's have the limit as x approaches 2, well, if we approach from the left and from the right, we're always approaching that spot right there. We're always approaching 3. And it didn't matter where on the line, didn't matter what limit I had, it's a constant function. It's always getting closer and closer to 3. The next one is the limit of x. So if I think of that as a function, that's the function y equals x, which is just a perfect diagonal. And with that one, if I want the limit as x approaches some number, I'm going to say 2 again. Well, from the left and the right, it's getting closer and closer to that point, which is also a y value of 2. That makes sense, right? It's that perfect diagonal, whatever your x value is, so is your y value. So those are the only two of our limit properties where we're actually going to get where it's giving us a number answer specifically. So we're going to have to break everything down into those two cases when we do our next example, which is a bit of a silly example, but I'm going to show it to you anyway. These next ones are how to break larger limits apart. So this one here says that if I have the sum of two functions and I'm taking the limit of it, then I can take the limit of the first part and add the limit of the second part. I'm allowed to do that. Similarly, if I'm subtracting, I can take the limit of the first and subtract the limit of the second. If I have a constant, there's that letter C in front, I'm allowed to pull that constant out. It's kind of like I factored it, right? The constant can come out in front of the limit and I can evaluate it that way. Number 6 is a lot like 3 and 4. If I have the limit of a function times a function, that's the same as doing the limit of the first function times the limit of the second function. Similarly, if I'm dividing functions, I can take the limit of those. 8's a tricky one, but we're going to see it in a minute. If I have the limit of something to an exponent, then you can just move that exponent to the outside, take the limit of the inside, and then raise it to the exponent. And then number 9, if you remember a little bit of grade 11 and some of your exponent laws and rational expression stuff that we did, writing things as a root is actually the same as writing things as an exponent, right? An exponent of 1/2 is the same as a square root. An exponent of 1/3 is the same as a cube root. So number 9 is really just a special case of number 8. Okay, evaluate the following using the limit properties. This is the long way. We are not going to do this very often. So we're going to try and think about all those limit rules that we had. I'm going to jump back and forth a little bit so we can see it. Notice this is just a quadratic. Okay, so a very simple function. It never has any breaks. It never has anything funky happen. The domain is the entire set of real numbers, so it goes on forever. We're just approaching x equals 3, so we're approaching some particular value in it. But if I want to use our limit rules, I'm trying to evaluate the limit of that. Well, we can think of this as a function plus another function, take away a function. And remember, rule number 3 and 4 told us what I could do if I was adding and subtracting functions. I'm allowed to break this up into its parts. So the limit as x approaches 3 of 4x squared, that's the first part, plus the limit as x approaches 3 of 3x minus the limit as x approaches 3. I'm going to put that in, oh, excuse me, I can just put a 5 there, of 5. Okay. So that was rule 3 and 4. The last part there, where it says limit as x approaches 3 of 5, that is rule 1, right? It's just a constant. So that's good. I'm going to be able to evaluate that one in a second. We'll do that, but we'll get there in a second. For the first two there, it's got a 4 and a 3. And those are the constants times a function. That's rule number 5, right? Some number times a function of x. And what we're allowed to do is we're allowed to pull those out. So I can pull the 4 in front. So, oops, not a 3, that's an x. And this last one I'm just going to leave. Okay, it's the limit. I'm going to evaluate it in a moment. So the last one with the 5 is just a constant. We can get that one. The middle one, right here, that's a limit of x, which was rule number 2. So we can do that one. The first one there, the 4 out front is fine, but it says limit of x squared. And that is rule number 8. It's some function squared, or some function to an exponent, I should say. So I'm going to take that squared, and I'm going to move it outside. It'll look like this. The 4 stays there. Limit as x approaches 3 of x. Squared goes there. Everything else is still the same, though. And now it's time to evaluate it. So, sorry, I'm going to back up for one more second. This should be last time. Sorry, I'm jumping around like crazy. We're looking now at just rules 1 and 2. Rule 2 in particular to start. The limit of x as x approaches a is just equal to that a value. So for this first one, right here, the limit as x approaches 3 of x. So we just sub in the 3. The 4 stays there. The limit gets evaluated to a 3, and it's squared. Plus 3 times the next one. There's our limit as x approaches 3 of x again, so that's just an x. Sorry about that. And the last one is just our constant, right? And it's just equal to 5. Sorry, I got mixed up when the smartboard panicked on me. Let me fix that last one. We said the limit as x approaches 3 of x should be 3, right? I've substituted that 3 right there. And I think I'm actually going to slide this note out for a second because I want you to see what's happened. We did a lot of good steps, right? We used a lot of those rules. But take a look at what it's all broken down to. In the end, compare those 2 steps. And really all we've done is subbed in the 3, haven't we? So it says if f of x is a polynomial, then the limit as x approaches a of f of x is just f of a. Right? All you actually have to do is sub in the value of a. And that happens a lot. So almost all of the examples that we're going to look at least the simple ones like this, you just sub in the value. Now I'm going to show you, part of today is showing you the special cases when it doesn't work, and that's what we have to focus on, of course. But this is how we're at least going to try and solve our limit problems to start. Let me evaluate this. 4 times 9 is 9 minus 5. What's that? 36. There's 140. So the limit's 40. So an awful lot of work there. We did it well, right? Used all of our limit properties, but in the end we could have just subbed in the a value. So here's our problem then. Is that sometimes we need tricks to evaluate some limits. So we're going to factor this. I'll show you why. Our trick, by the way, is factoring though. Here's our expression. Don't write this down, but I'm going to show you what would happen. If we thought of this just like the last example, we could try breaking it up using all of our different limit properties, right? Oh, it's a function divided by a function, so we'll split that up and so on. But for the most part, all we're going to try and do is sub in x is 4. So if I do that, this is what would happen. Again, don't write this down. So this is skipping a whole bunch of steps, right? But assuming that what I should do is just end up subbing in the 4, I would get that. Now if I evaluate the top, That's 16 minus 28 is minus 12 plus 12 is 0 over 0. And that's a real big problem. 0 over 0 doesn't tell us much. 0 over 0 is something called our title there, which is an indeterminate form. And an indeterminate form means there's some information there, we just haven't been able to figure out what it is yet. 0 over 0 is frustrating. It's not the same as something like this. If I have 0 over 5, that's just 0, right? That's just 0. If I have it the other way around, 5 divided by 0, we say that's undefined. And these are the ones that we've talked about in the past with you guys. That 5 divided by 0 is a fairly big concept in grade 9, right? That idea of an undefined slope. But we never really deal with 0 over 0. It doesn't have much of a context until now. So 0 over 0 is something called an indeterminate form. Now, fortunately, you guys actually did some of this back in grade 11 when you dealt with rational expressions. Let me get this out of the way so I can get a little more space. If you have that expression, we can factor it to try and reduce it. So I'm still leaving the limit. If I factor the top, I need two numbers that multiply to 12 and add to minus 7, right? So minus 3 and minus 4. All over minus 4. And then conveniently what happens is we've got an x minus 4 on the top and an x minus 4 on the bottom. So those are going to cancel out. And it leaves us with just x minus 3. Well, now you can substitute that in because it's a really simple expression. And our answer is just 1. So that's how our factoring works. But we should probably think a little bit more about why that happened. With rational expressions from grade 11 again, what we're saying is that this expression right here, this big one, is exactly the same as this one. They are equivalent, except for restrictions. And our restrictions are values that the denominator can't take on. So our restrictions in this case were, well, it's directly from that x minus 4. The restrictions are that x can't be 4. Makes sense, right? I mean, we tried subbing in 4 and we ran into problems. So we're saying that those two expressions are equivalent, but x can't be 4. Is that a problem then? Because down here, I subbed 4 in to evaluate the limit. And that, I don't know, that seems like a problem, but it actually isn't. Remember, when we're evaluating a limit, subbing in 4 is our shortcut. But really what we're doing is we're saying what happens as x gets closer and closer to 4. We never get there, right? We get to 3.9999999. And when we get to 4.00001, we get really, really close to 4, but we never get to 4. So who cares that the restriction isn't 4? We're not getting to 4 anyway. We're just getting really, really close, which means this is allowed. We've done nothing wrong here. If you wanted to think of this graphically, that big function up top, x squared minus 7x plus 12 over x minus 4, reduces to x minus 3, which is just a straight line, right? Y equals mx plus b. It has a y-intercept of minus 3, and it has a slope of 1 over 1. So the graph would look like this, as a straight line, except then your restriction kicks in that says x can't be 4, right around there. And so right there, we've actually got a hole, okay? So right at x equals 4, nothing exists. So this expression up top, that function, is that line with a hole in it. And I think you guys did a fair bit of stuff with advanced functions with that too, looking at holes and asymptotes and that sort of thing. Okay? Did I ever make a mess of that? My goodness. Okay, I'm going to try and get rid of all of that, and then we'll try going on to B. Same idea. We should consider substituting in first as a way of solving, but you might be able to do that in your head, right? If you sub minus 2 into the bottom, You get minus 2 squared is 4, 4 take away 4 is 0. So there's our first problem. We've got 0 on the bottom. It isn't actually a big problem unless the numerator is also 0. So minus 2 squared is 4. You get a 4 there, minus 20 there, and a plus 16, so that's 0 again. So we would get a 0 over 0. So we're getting an indeterminate form again. Oops, that's not spelled very well. Indeterminate. There we go. So we should try and factor. The reason we sub in is sometimes it'll just work, right? Sometimes you can just sub in and you get a nice number. It's only if you get 0 over 0 that we actually have a problem. And yes, I'll probably try and trick you at some point and make a nice easy one and see if you catch it. If we factor the top, x plus 2 and x plus 8. The bottom's a difference of squares. And this is what we needed to happen, right? We needed to have those x plus 2's. The problem happened because we're subbing in minus 2, right? So if I can get rid of the x plus 2's, that's where the 0 is coming from. So those cancel. Leaves you with x plus 8 on the top and x minus 2 on the bottom. And now we can just substitute. So like I said, to finish out these limits in the end, we just substitute in. We just have to be really careful that we don't substitute all the time right at the beginning in case we get that 0 over 0. What's that? 6 over minus 4. So minus 1.5. Here's our limit. So the 0 over 0 suggests that, well, it just says we don't know too much yet, right? We have to do more work before we can figure out the final answer. Okay, so method number 1 is factoring. Method number 2 is rationalizing. So rationalizing is probably the trickier one because we can come up with some more difficult, more difficult expressions for it. Rationalizing is a way of trying to get rid of roots. And it's a neat trick. It works really, really well. It's almost a factoring sort of idea. It's taking advantage of some of the factoring principles at least. By the way, I should mention this may come up occasionally. Another way to sometimes help evaluate these is sometimes to expand and then cancel things out. So you'll see that occasionally too. These will be the ones you see more often, but occasionally expanding and canceling will also work. Okay, so if we want to rationalize, I'm not sure how much of this you'll remember, so just in case. The idea with rationalizing is you start with the same expression that you had originally. But we're going to multiply it by another fraction. And what we multiply by is we multiply by the root that we had. So we multiply by this expression, except we change the sign in the middle. So we're going to multiply by root x plus 1, right? That's the same. But then instead of minus 2, we multiply by plus 2. And we're going to be allowed to do this as long as the denominator is exactly the same. Because technically now all I'm doing is multiplying by 1. All I'm doing is multiplying by 1, which is allowed. And forgive me, I should have mentioned this. I never even talked about what would happen if I subbed in x equals 3 in the first place. Or maybe you noticed it. If I sub in x equals 3 to this first expression up at the top, the denominator would be 0, 3 minus 3. Numerator is 0 as well. 3 plus 1 is 4, square root is 2, take away 2 is 0. So we do get a 0 over 0 from there. So we have a problem. We're going to try and work with this rationalizing idea though. And here's where part of an expanding idea comes in. I'm going to get rid of this guy. We kind of have a binomial, two things, times another binomial there. And I'm going to just multiply them all together. So I have to do everything in the first bracket times everything in the second bracket. So multiply those together, and then minus 2 as well. So when I do the root x plus 1 times root x plus 1, that's a square root times a square root. That is just x plus 1. There's our first one. The next one is root x plus 1 times plus 2. which is just 2 root x plus 1. Here's the good part. The next one is minus 2 times root x plus 1. And so hopefully you can see what happens there. Those middle terms are going to disappear, right? What we've done by rationalizing like this is we've created a difference of squares scenario, right? The plus and the minus, which is going to allow the middle terms to cancel out. So that's why we changed the sign, was specifically so that we would make this happen. The middle two terms would disappear. The last one's a minus 4. Now on the bottom, technically you could expand this if you wanted to, right? It's an x minus 3 and then a root x plus 1 times plus 2, or plus 2. But it's not going to help. Okay, we're never going to expand. Well, I should never say never, should I? We're generally speaking not going to expand this one. And you'll see why in just a second. The problem is the 3 value, right? If we sub in x equals 3, we get a 0, which means this guy right here is the problem. We need to get rid of him somehow. And that's almost there. Still limit as x approaches 3. I'm running out of space, but I think I'm going to be okay. The top, those 2 roots are gone, right? The plus 2 and the minus 2 cancel. Then we have an x plus 1 minus 4. Well, that's just x minus 3. That's convenient. And on the bottom, x minus 3 times. And so now what happens is those 2x minus 3's will cancel. And if we'd expanded the bottom, we wouldn't have noticed that. So that's why we really didn't want to expand that part. Be careful when you cancel that top. There's still a 1 there. Right? You're dividing both the top and the bottom by x minus 3. And when you divide, it leaves a 1. And now we're okay. Just barely had enough room to. If we sub in our 3, what's that give us? 1/4. That's rationalizing. Okay, we're taking an expression and multiplying it by an expression that creates a difference of squares for us. Okay, last one. If you can, give that one a shot without me, and then you just pause it and see if you can pull it off. But it's the same problem again, right? If I sub in 0 right now, we obviously get 0 on the bottom, and on the top we get square root of 2 minus the square root of 2. So we get 0 on there too. So what we're gonna have to do, I think I'm gonna try and save some space. I'm gonna rationalize right away. So I'm gonna multiply this by the first bracket, or excuse me, the first square root was just x plus 2. The second square root was 2 minus x. And the key is that sign in the middle. Right? It was a minus. I need to change it to a plus. So technically I'm multiplying by 1/1, which is fine. And now we'll see what happens as we expand. Remember the denominator I'm going to leave, but the numerator, sorry, there's a lot there now, isn't there? I need to multiply everything in the first by everything in the second. So the first one is root x plus 2 times root x plus 2, which is just x plus 2. The next one, and I guess we'll show it. It's going to be plus root x plus 2, the first square root, times that square root at the end, right? This one right here, root 2 minus x. But then here's that good part again, right? The next one, we're multiplying this by this. Wow, I'm making a mess when I do this, aren't I? So that's minus root 2 minus x times root x plus 2. And those middle terms are going to cancel again. Here's one you got to be really careful with. This is going to catch some people. It usually does. The last one there is a minus root 2 minus x times positive root 2 minus x. That's a minus all of 2 minus x. And I put those brackets there because I need to remember that that minus sign is going to affect both of those 2 and the minus x. Denominator we said stays the same. Okay, so on the top, that and that are gone. That was the good part. That was what was supposed to happen. Otherwise rationalizing didn't go too well. So we approach 0. And I think I'm gonna take this. Oh, let's take it slow. What do you say? Multiply that minus in. So minus 2 minus x. Oh, there I did it myself. Plus x, right? Minus times minus. Divided by. So the top, what happened? The 2's are gone. But x plus x will be a 2x. And now we've got an x on the top and an x on the bottom. So those cancel. That was what I needed to happen, right? Because we had the limit as x approaches 0. So just having those x terms was what was causing all of the problem in the first place. If I sub in the 0, it's going to be root 2 plus another root 2, which is, but I got this out of the way, just 2 over 2 root 2, which is 1 over root 2, and I'm very happy with that answer. Although I think Mr. Vandenberg showed you guys a little bit how to simplify that. You can write that as root 2 over 2. But honestly, I don't care if you got to there. I'm a very happy camper if you got to there. Okay. That's probably our first limit actually that didn't turn out nicely. We didn't get a real nice number at the end. We got a root, but that makes sense, right? I mean, we were dealing with a whole bunch of square roots, so it shouldn't surprise us that the answer wasn't real nice at the end. So there you go. There's those are our ways of evaluating some limits of indeterminate forms, right? One method was factoring. We said sometimes you can expand. That's a good method too. And rationalizing is a big one. Rationalizing is probably the toughest. So as you're practicing today, just pay close attention to the rationalizing stuff. That'll be the one that sometimes causes the issue, especially like I said at the end here. Watch out for those minuses. Okay, multiplying them through the brackets. If you forget that, you can still get answers. So it's not like the whole question blows up on you. It just turns out to be a wrong answer, unfortunately. So be careful.